Okay, good. So we're ready. The next speaker is Inderjit Dhillon, and the title of his talk is Exploiting Primal and Dual Sparsity for Extreme Classification.
Okay, thank you. Let me just make sure I send the right slides. Okay. Because I remember going to a workshop, I don't know, 4 or 5 years ago. There's a well-known professor, I won't name him. I was chairing the talk, and he started giving his talk. I introduced him. And then after a minute into the talk, he said, oh, these are the wrong slides, wrong talk. So even the title was different. Anyway, thank you for giving me the chance to give a talk over here in this workshop. Today I'll talk about extreme classification, both for multi-class problems and for multi-label problems. And what we'll do is try and exploit primal and dual sparsity for such problems. I've actually been interested in these problems for quite a few years. A couple of years ago, we had a paper where we were looking at correlations between labels and exploiting them using a low-rank framework. That does make a structural assumption on the data. So this work is trying to get rid of that structural assumption. So this is joint work with Ian Yen, Xiangru Huang, Kai Zong. Kai Zong and Xiangru are in this conference, and Pradeep Ravikumar. So when this paper was written, we were all at University of Texas at Austin. Since then, we've spread out, and we are in different places. And this work is really the work of my students. Ian would have been the right person to actually give this talk, but he was not able to get a visa to come over here. So I am the messenger and conveying the work that the students have done. Okay, and this work, we've been doing ongoing work, but this paper appeared in ICML earlier this year. So the obligatory motivation, you have many, many different categories now in ImageNet, 20,000 plus, a multi-class problem. Wikipedia, you have more than 1 million categories, but each article has a label, so it's a multi-label problem. So the goal over here is that we have d-dimensional data. D can be quite high because my x's could correspond to, for example, in the Wikipedia article, they would correspond to words that appear in the collection of these articles. So the dimensionality could be quite large in the millions. And then what is sort of new in this extreme classification is that the number of classes or labels can also be very big. So what we are trying to learn is a function h that takes an input sample, let's say a Wikipedia article, and maps it from d dimensions to k dimensions. Okay? So these would be the k output scores, and there's labels. We'll encode them as 0, 1s, and we'll sort of make the assumption throughout that for a particular sample, there are only very few positive labels. Okay? So for each sample, it only belongs, well, in the multi-class setting, it only belongs to one class. But even in the multi-label setting, we are sort of we will make the assumption that the number of labels that it belongs to or it should be given is much, much smaller than the universe of all labels, which is k. Okay? So just to set some notation, k will be 1,000 to 1 million. Py is the set of class k's such that yk equal to 1. So in multi-class, the size of py is 1, and the negative labels are the complement of the positive set. For today, I will just consider linear classifiers, and we'll see how one can achieve speed up by using linear classifiers. In principle, it can be extended to a non-linear setting via use of feature mappings, but one would have to be obviously cognizant of computational considerations. So, the standard approach, one way to approach this problem, again, is to think about just using one versus all, even when k is very large. The problem with this approach, of course, which can be mitigated, as we saw in the earlier talks, by doing distributed computation, but the issue is that the training time and the model size will generally scale linearly with the number of classes. Okay? And that can be prohibitive. So for example, in this Wikipedia data set, if the number of classes is 300,000, more than 300,000, then if you just take the time for binary classification and multiply it by 300,000, it's just going to take an exorbitant amount of time. So the question that Ian and the rest of us asked is, can we try and have prediction training as well as prediction time and the model size that does not grow linearly with the number of labels? And in contrast to the previous work that me and my students did, which was called LEML, can we get by without structural assumptions such as either low rank or that there's some tree structure, for example, on the classes? So here's a little pictorial that we try and justify the use of max margin loss as opposed to a one versus all SVMs. So you should think about, let's look at the left plot. We have given here, Z is the scores that you get. If this is a positive label and the score is low, then one versus all will penalize it, SVM. And the reason we have drawn it like this is you can think of these are sort of independent computations, independent SVM computations. So think of each vertical line as one different SVM computation. And what happens is that when you take a point, then the number of support labels might actually be very large. Okay? So there is no inherent sparsity in what we'll see in the dual variables which correspond to the support labels. On the other hand, if we use a max margin loss, which I think was also talked about earlier, then there is some inherent sparsity. There is no loss in this case when, for example, all the positive labels have higher scores than the negative labels, plus some margin. But otherwise, there is going to be sparsity. The number of support labels is generally going to be much smaller. So what we are interested in, are making one assumption, which is, I think, reasonable, that the number of support labels is going to be much, much smaller than capital K, which is the total number of classes or labels that you can give. So just sort of to leap ahead a little bit and tell you about the results that come from this max margin approach, I will talk about how we get to this. So we have experiments here with DMOS and the Wiki data set. The Wiki data set has 2 million samples. The number of labels is 300,000 or more than 300,000. The number of support labels is much, much smaller than the number of labels. Okay? And as a result, not directly as a result, as a consequence of this and as a result of doing the work that I'm going to talk about in the next 20 minutes, we can get the following performance, which is on the table, the second table on the left-hand side, which if we were to do one versus all naively, okay, obviously, we have multi-core machines and we can speed it up, but if we were to do it naively, then it'll just take a very, very long time on these data sets. But if we use our method, which we call PD sparse, that stands for Primal-dual sparse, then the time is much less, and it's a consequence of the number of support labels being much smaller. So what we are going to do is, so this observation has been made before. What we are going to show is that we can actually exploit the fact that the number of support labels is smaller by being able to find sparsity in the primal. Okay? So we'll not only have a sparse dual solution, but we'll also get a sparse primal solution. And so we'll show that there is an optimal model, W star, where whose number of non-zeros in that model, remember we are just using a linear model, will only scale with the number of support labels. So let's talk about that. So just to revisit, the max margin loss is given over here. So remember, for example, there will be no loss if all the KP is an index that belongs to the positive label set. Kn is an index that belongs to the complement of that set. And if all the positives have a higher score than all the negatives with a margin, then there'll be no loss. But otherwise, if they are flipped around a little bit, or even if they violate the margin, then there will be a loss. Okay? So the W star that is obtained from the minimization of this max margin loss will be determined by the scores of the support labels. And the support labels are going to be this pair of indices, which are the result in, it's the argmax of this loss for a particular label. So when you look at this problem and it's dual, what you can show is that the optimal, so if I take a particular instance, then let's suppose the number of support labels there is lowercase k. Okay? And we are making the assumption that lowercase k is going to be much, much smaller than uppercase k, okay? Which is the total number of labels. And then when we ask the question, what is a W that could sort of achieve this, we can actually see that it's actually going to, it needs to satisfy a much smaller set of constraints. These are just linear constraints that should be satisfied at the optimal, which means that if I look at so if now I say that Ka is the average number of support labels per sample, okay, then my W star, remember W is, the dimensionality of the data is D, and I have K classes. Okay? So my W is actually a D by N weight matrix. Okay? But you can show that, sorry, did I say D by W? So D by K weight matrix, W is D by K, and when it is much bigger than the number of samples times the average number of support labels per sample, that means that there are many, many parameters in some sense that are free. Okay? In particular, you can think of this as a linear system of equations where you have n times Ka equations, but the number of variables is D times K. So it's a very severely underdetermined problem. There's a lot of flexibility in choosing W star. And so in terms of being able to do things more efficiently, we can ask the question, can you try and find a sparse W star with a minimal loss? Okay? So it's posed as a question. I'm standing before you. The answer is yes, we can do that. And that'll be, in some sense, the key to getting good complexity. So when we try and find a sparse, or when we look for a sparse W star, the natural thing is to put a sparsity preserving regularizer. We are not making any other structural assumption than sparsity. So we can use the L1 norm regularizer. And what you can show is that if things are in general position, that means things are not degenerate, right, where somehow the effective number of variables is the same as the effective number of constraints. But if things are in more general position, then what you can show is that, and Ian has used the terminology N and Z to say number of non-zeros, and that will keep on appearing through the talk. Okay? So N and Z is the number of non-zeros in the primal optimal solution. And N and Z A star is the number of non-zeros in the dual optimal solution. So what I said before was saying that, well, we assume that the number of support labels is small. So if you look at this picture on the right, that means that if I look at a particular, this is n by k, so each row is k-dimensional. So there will only be a small number of non-zeros in each row. Okay? Those will correspond to the support labels. And what we are, the consequence of this theorem is that we can actually go ahead and then find a W star where each row is also sparse. Well, remember what W is? It's a D by K matrix, okay, of weights. And so each row here corresponds to features. So what it's saying is that there is just a small number of non-zeros associated with each feature. And that's a consequence of this, which says that the number of non-zeros in W star is actually less than equal to the number of non-zeros in A star. Okay? So now we are looking for a sparse, and of course, these are the primal variables, and A is the, I don't know what is capital for alpha in Greek, but we used A. Okay? But it stems from the dual variables alpha. We are looking for these sparse solutions. Okay? But we can only be effective if the algorithm actually keeps sparsity at all the intermediate steps. Right? It's not enough to just converge to a sparse solution at the end, and in the intermediate steps, you have a dense W. Okay? So otherwise, we'll end up using a huge amount of memory in between. In the computation, we might be able to compress the model later, which I think was alluded to by the previous speaker. But this is saying that throughout the algorithm, can I sort of maintain sparsity? Now, for ease of implementation, and for some other reasons, we include the L2 regularized objective also, right? So to make it the problem strongly convex, the dual problem strongly convex, does not really hurt the sparsity much. And then here are, when we solve this problem, right, using the algorithm that I'm going to hint at in the next couple of slides, then here is in the table over here, you can see not only the number of support labels per sample, so those are the number of non-zero dual variables, but also the number of non-zeros per feature. And those are the primal variables. Okay? So those I denote by Ka and Kw. And you can see on the left-hand side, we've listed for each data set, we've listed the total number of classes. And you can see that Ka and Kw are generally much smaller than the total number of labels or classes. Okay, so how do we, after making this assumption, like I said, we have to somehow keep sparsity, okay, throughout the course of the algorithm. Okay? So when you sort of look at the dual form of this this problem, which has L1 regularization as well as L2 regularization, then you can write it in this particular form, and it is a smooth objective, okay? And what you have is block separable constraints. Okay? And so the natural idea then is to minimize with respect to one alpha I at a time. Remember, alpha I is now the dual variables that correspond to each example. Okay? So the question then becomes, how do we efficiently find the support labels and the active features? Okay? So not only do we need to find a sparse A, but we need to maintain a sparse W also to search through my dual variables effectively. Okay? So we, or rather Ian, employed a block coordinate Frank-Wolf algorithm, and he made me this nice slide. I don't know if it was in the paper or not, but so this sort of captures the computation that is done at various steps of the algorithm. How much time do I have? Okay, I think I'm good. Okay, so what happens is we start, for example, with a 0 W, or W being all zeros, alpha being all zeros. In the beginning, at some stage when there are some non-zeros, I will have a gradient. I can select the most violating label. In the beginning, I can just select a random label. I find out what alpha I am updating. I do this projection and the update. So I'm incrementally adding labels, but remember, I can drop some labels also because of this projection operation. Once I have delta alpha, that means a change to the dual variables, then I need to try and find the corresponding primal variable. Okay? And the corresponding primal variable is formed by this proc step, which was meant to make it sparse, right? There's a sparsity promoting regularizer. And so what we do is we essentially search the active set AI via a sparse A, for sparse W. And we, throughout this algorithm, of course, have to use sparse data structures, right? So we use a compressed row storage form for storing A, and we use also a sparse matrix representation of W. Okay? And you have to be a little bit careful in the implementation, but you can actually maintain sparsity. You have to access W and A in a particular way. I won't go into details, but the cost then is, the number of non-zeros. And of course, many times these methods are applied to text data sets where my X is sparse. So the cost per cycle is actually proportional to the sparsity in the X, okay? in the data point. Okay? And so by doing this, so you do this basically per sample. You do this cycle per sample. So when you make a single pass of the data, the amount of work that's required is the number of non-zeros in the matrix X, which is the matrix of all the samples, times the average number of non-zeros in the primal, plus the number of non-zeros in the dual. Okay? And this sort of method then converges to the solution which is sparse. Okay? Now, one thing you will notice is that I showed the result for the results. The sparsity result is for the primal optimal and the dual optimal. Okay? And you might ask, well, is there any guarantee that the intermediate W's and the alphas, or the A's, are also guaranteed to be sparse? I don't have a theorem, sorry. Okay? But empirically, we find that the intermediate W's and the A's that we find are actually also sparse. So here are experimental results for the multi-class setting. The top figure, accuracy. So the top panel is LSHTC1, which is the smaller of the LS datasets. Accuracy, you can see that PD sparse is fairly competitive with one versus all SVM, slightly lower accuracy. The training time is comparable to some of the tree-based approaches, can actually be sometimes better. But the prediction time is better. So if you look at, for example, DMOS, the data set, the accuracy is actually higher in that case. Remember, the times are, I don't know if you can see clearly, but the times are actually on log scale, okay, in the training time and the prediction time. So because of the sparsity in W and the sparsity in X, the sparsity in X is also important over here, that many times you actually do not have to, when you do this testing, when you do the prediction, you're actually not searching through all the labels. You only end up searching through the non-zeros that are produced, and that can be sublinear in the number of labels. So in conclusion, PD sparse can reduce the training time and the prediction time by orders of magnitude without sacrificing the accuracy. And then on multi-label data sets, this is the big wiki data set, LSHTC. You can again see that we get better accuracy. The training does take some time, so I'll talk a little bit about how to speed that. But the prediction time is very fast, okay? And this is a consequence of the fact that these are the test point, or the X is also sparse over here, okay? So this is actually mainly a summary of the ICML paper, and then we've been doing some more work on this. So one thing that is obvious that somebody will point out, and it's already been pointed out in the talks that have occurred before, is that, well, one versus all is sort of embarrassingly parallelizable, right? So you can throw 1,000 cores, many cores, whatever number of cores you have, you can throw at that problem, and you can parallelize it, okay? So then the obvious question is, well, what about parallelization of the method that we have, okay? Well, if you look at the Hessian of the dual problem, okay, the Hessian is block diagonal, where the number of blocks is the number of labels, okay? And the number of possible classes, of course, is very big, okay? So what one can do is that, if you're handling one sample and you're handling another sample at the same time, they will only sort of have a collision or conflict only if they are, getting confused with some other block, okay? With the same class, with the same label. And in general, when K is very large and Ka is small, what we can have is order K divided by Ka threads without hurting convergence, okay? So Ian is still sort of working on it, so we don't actually have the timings, but what he has shown on this figure is that the number of epochs, as I increase the number of threads, does not increase, so the convergence is still good, so I can actually parallelize all these without hurting convergence. So what this says is, in this left figure, you can see that up to 100 threads, there is no loss in the number of, no increase in the number of epochs. But if I go to 1,000 threads, yes, I will lose a little. So if I have 100 threads, yes, I can get parallelism. If I have 1,000 threads, I might lose a little bit of speed up. On the right side is a smaller data set where K is smaller, but Ka is comparable. So K divided by Ka is not so big. So in that case, we actually do lose quite a bit in parallelizing, right? So when the number of classes is much, much bigger than the average sparsity, then we can parallelize and be very effective. So I know that I'm running out of time. I'll just quickly go through this. Of course, we may want to have like a more robust measure of loss. So instead of this max margin loss and just looking at the argmax, I can actually just restrict ourselves. We can restrict ourselves to the top R margin loss. Okay. So when capital R is 1, I get back the max margin loss. When capital R is capital K, then I get 1 versus all. Okay? So we haven't actually done any experiments with this, but this is one way to, guard against mislabelings. And then just to give an advertisement of a talk that's coming up, one thing that we did was realize that we can actually also handle structured classification with sort of a similar setting. So there will be a later talk. At what time? In an hour or so? 2 hours? I don't know. Okay. Later today, okay, by Shangru, who's a student. Okay. In conclusion, this extreme, when K just becomes very, very large, on the face of it, it seems like a bad thing, but it actually turns out to be somewhat benign. Okay. Not only is there dual sparsity, but you can actually have primal sparsity. We can now get an algorithm that empirically achieves complexity which is sublinear to the number of labels. We don't sacrifice accuracy. Prediction time is very good. We are working on speeding up the training time, and my goal in this project, and I've told Ian, the goal is not necessarily to publish papers, but to make Manik happy. Okay, and Manik is a tough person to please. So whenever we show him some work, he's always saying, "Well, you should increase training time, or prediction time, or model size." So hopefully we'll achieve it someday. Okay, thank you.
We have a few minutes for questions. Manik, are you happy?
No. Manik, he will ask me offline, don't worry. He will send me lots of emails.
Yes.
I think the question was something about how do I handle in these steps that the number of when I look at argmax, there might be more than one pair or many pairs that have this problem, and how do we handle getting stuck in some degeneracies? Honestly, I don't know, right? And Ian can answer the implementation questions. I don't necessarily see any, obvious issues. If there are more than one violating pair, then we'll just have more number of dual variables that are non-zero. So I actually don't see any issue with that. I don't know in the code how he handles it, but in terms of optimization, I don't see any issue with that. So the question is to say whether there's anything in the code that sort of ensures whether we are making enough progress, right? So typically when we are doing ascent algorithms, then we have either some step size search or so, which ensures that we are making enough progress to the solution. Yeah, I don't know what safeguards he's taken. Yeah, we can take it offline.
Okay, let's thank Inderjit again. And